Hey, okay, students, why don't we do some more examples here? I just did these four, and so let's do another four here. And maybe I'll begin like I did these other ones, and those I talked about mirrors. And here was our little discussion with our mirrors. And why don't I go ahead and do a comparison? This is good to see because the concave mirror, so these three options, are a lot like the convex lens. And so let me put a focal length, and something to keep in mind is that the focal length, there's one on each side. If you remember the equation, so here it is again, for the focal length for a lens and a thin lens that's in air on both sides, would be given by this equation. And so it depends on the curvature of each of them and the index of refraction. And if you were to, shine light in one direction, it would converge at some point called the focal point. But if you do it the other way around, the light would, of course, now converge here. So that's why there'd be a focal point on both sides. And numerically, they are equal conceptually because they go through both surfaces, whether they go left to right or right to left. And then, of course, mathematically, you can see that if you interchange 1 and 2, of course, it almost looks like you get the negative of it, but you have to remember the definition of a positive and a negative R. So when you flip the lens around, you are, what was positive now becomes negative for R and vice versa. So these switch orders and they switch sign, which makes the equation exactly the same. So it's a focal length. And in fact, you could even think of the mirror as having two focal points because the light actually comes in, so it goes by the focal point, then it bounces off the mirror and goes by the focal point again. So that same focal point serves as, the light coming in and the light going out. And that's what you have here when you have a lens. The light comes in and then the light goes out, and so you have the two focal points. So in viewed in that manner, you begin to see why we can say that a mirror has two focal points, whereas a lens has two focal points. And, of course, for the mirror, they'd be the same value. And, of course, for the lens, they would be the same value, if that helps at all. But if you look at these cases that we talked about, these two are kind of essentially the same. And then this one, so I don't know if you want to call it 3 or 4. I like to call it 3, or your author calls it 2. But to kind of illustrate that, let's do double the focal length. Here's where for the lens, doubling the focal length doesn't make any sense, except mathematically it does, because then it matches these two really well. And what it means, if you have your object out here, so double focal length, and again, we wouldn't want to call it the center of curvature, but what it would mean is if you come in and go through the focal point, or if you go through the focal point and then go straight, you're going to get an image here that is upside down and smaller, and it's between the focal length and twice the focal length. And so that represents case number 1, where you get a real image, it's upside down, and it's smaller. Whereas if you put the object here, which is between the focal length and twice the focal length, and you draw your ray diagram, you'll get a real image, again upside down, but now bigger. And really the position of the object and image just inverted, as you can see in the math and as we talked about for the mirrors. So there would be the connection between those two. So that's 2 of the 3 possibilities you can make with a converging lens or a converging mirror. And so concave mirror or convex lens. And they're both converging. I kind of like that phrase, converging. That's the way I can see how the same physics applies to the lens, the converging lens, and the converging mirror. But geometrically, they're different, concave versus convex. Now, the last scenario with this lens is the one where you put the object in front of the focal point. And so the light that comes in here goes through the focal point. And like we did back in this first case, you can't really draw the ray that goes from the object through the first focal point because it doesn't go through the mirror, but you can draw it at the angle as if it came from the focal point, and then it would go parallel. And that means somebody standing over here on this side would see these light diverging and would trace them back to a point that they didn't really come from, but they appear to come from, hence image, and hence virtual image. And so this would make it upright and bigger and virtual, and that's what is the connection between this case. So the converging lens or the convex lens has the three cases: upside down smaller, upside down bigger, both real images, and here right side up and bigger. And this is the magnifying glass scenario. And then, of course, the fourth and final case is the diverging lens or the concave lens, and it acts just like the diverging mirror or the convex mirror. They each have a negative focal length. You can see that in the math when you apply this here. This R1 would be a negative, and then you would subtract R2, but R2 would be a positive, so you got two negatives, and overall then that makes the focal length negative. So with our negative focal length, although physically it would have some kind of length, it would just mean that no matter where you placed your object, the light would then spread out as if it's coming from that virtual focal point, or the one heading towards this virtual focal point would bend out and go straight, and then it would appear to be coming from right here, and so you'd get something that's right side up and smaller and virtual. And that's the only thing this lens can do, and that's what this lens did. All right, well, I hope my little mini lecture didn't waste too much time. Let's jump into the problem. And I printed these up somewhere. Aha, here they are. And so here is number 34 on my list. Let's give that one a try here. But it says the projection lens of a certain slide projector has a single thin lens. Okay, so we can use the thin lens formula here. The slide is 24 millimeters high and is to be projected so that the image fills the screen that is 1.8 meters high. Now, I'll pause right there and come back to my little drawings here, because if we're going to project something on the screen, we want the light to actually hit the screen, not appear to be coming from there. It's not like somebody's looking into the lens. So these two scenarios, which are virtual images, you can only see as you kind of look into it. It's where the light appears to be coming from. The light never appears there. If you want to put it on a screen and you want it to reflect off and then people to look at the screen, that means the image and the light has to be on the screen, and that's called a real image. So we have to have one of these two scenarios. This is where we'd place the screen. We'd put the screen right here, and then in that case, we would have an image that's upside down and smaller. Here, we can have an image that is upside down and bigger. So if I read this, we want it to be, I think, bigger. Yeah, see, we want it to fill the whole screen. We want it to be 1.8 meters high, and the slide is just this little tiny thing, okay, about an inch tall. So we want it then bigger, and so this is the approach we would have. Now, don't worry about the upside down part, because really what that means is we'll put the slide in the projector upside down, so that when it gets displayed and people are looking at it, it's right side up. And these old-fashioned slide machines, it's always easy to forget. You you're kind of looking at the slide and kind of getting your presentation ready. And as you stick them in, you're just a human tendency to put them right side up. And so most of the time you remember, and you put them upside down as you're going through your slides. But one of them you put in upside down, and then when you're going through your presentation, you go click, and it's upside down. You go, oh, shoot. And then you have to back up one so that you can access it and take it out, flip it over, put it back in, and go back. So these days with computers, you don't really see slideshows anymore. Okay, so anyways, we're definitely looking at what I'll call case number 2 here. Upside down, bigger, and a real image. Okay. The slide to screen distance is about 3 meters. Then it says determine the focal length of the projected lens. Okay, so we better come up with a positive. And how far from the slide should the lens of the projector be placed so that the image is on the screen? All right, so going through the math, here we got number 34 here. We have 1 over P plus 1 over Q is equal to 1 over F. Okay. Now, the other relevant things is the magnification. Height of the image is to the object as negative Q over P. And in this case, it's important then to realize that this magnification needs to be the height on the screen, 1.8, compared to the image, 0.024. So I'll change that, the millimeters here. And so we've got meters over meters. But like I said, this one, if you're not careful conceptually here, realizing we need it on the screen, you might miss that the magnification needed to be a negative number. That is, we have to have Q positive and P positive. And you don't really see that in there. They just say it's going to fill the whole screen. They don't tell you anything about upside down. They're going to let you figure out from the property of lenses for that case. So grabbing my calculator here, I will go negative 1.8 and divide it by 0.024. And so we're going to magnify it by 75 times. And the negative means we've got to invert it. Now, the other piece of important information here is they say the slide to screen distance is 3 meters. So coming back to here, we've got the P plus the Q, and I'll call that then the distance between the objects. And so remember, this distance here is for positive P, and this distance here is for positive Q. So adding those two together is the distance between them. Unlike a problem we did earlier, because of the reflection of the light, and P was measured positive this way and Q was measured that way, we said that the distance between them is P minus Q. So that's how it worked out for the mirror. But here, the distance between the object and the image is an addition sign. And then this said something like 3 meters or something. The distance is 3 meters. So there's 3 meters. But it's these two equations that allow us to solve for P and for Q. So maybe I'll take this first one here and then say Q then is equal to 75 times P. And then I'll use that over here to say I've got P plus a Q, which is 75P, has to be 3 meters, or 76P equals 3, or P is, and so I'll go 3 divided by 76. And so 0.039, I'll round it to a 5 meters. Maybe I'll even change it to 39.5 millimeters. Which, of course, means Q, we can get up here, would be 3 minus our last answer. And so we're looking at about a 2.96 meters. So most of the distance is all about Q. And so in reality, what we have is a lens. We got really kind of a short distance to the slide. And then this is probably the projector system. And then most of this is the 3 meters, just shy of 3 meters from the lens out to the screen. So there's our projective system. Let's see. So what do they want us to determine? They want us to determine, the focal length. I haven't done that yet. But how far from the slide should the lens of the projector be placed? So I did get the P already, but now let's do the focal length. And so 1 over P plus 1 over Q is equal to 1 over F. So let's see, this was my P. So let me take that number and then the reciprocal. Let me add it to the Q, that's that number, and then reciprocal, and hit enter. So that's all of that good stuff, and then take the reciprocal out of that. And so we're looking at a focal length that is just under 39. I'll call it 39.0 millimeters. I think that's right. 39, yeah. 0.0 millimeters. And let's see, P should be just a hair bigger. Yeah. So this is like that magnifying one, if you watched my little lecture on the magnifying P. So we're talking about the object just beyond the focal point right there, because that's where you get the most magnification. The closer you get it to that, the more the magnification is. And we're magnifying it quite a bit, 75 times bigger. We'd actually have to have a good quality lens, and otherwise that would get blurry. Okay, well, there's the first one. And I'll call that number 1. Second one on my list looks like number 36. So 36 says that we have an antelope at a distance of about 20 meters from a converging lens that has a focal length of 30 centimeters. Oh, okay, so maybe this is a camera lens, maybe a telescopic lens, and looks like we're trying to take a picture, some wildlife photographer. We've come up on an antelope, and we're going to take a picture of it. So the antelope is about 20 meters away. We have a converging lens, has a focal length of 30 centimeters. The lens then will form an image of the animal. Now, if the antelope runs away from the lens at a speed of 5 meters per second, how fast does the image move? Does the image move towards or away from the lens? So the picture, I guess, looks something like this. I'll put a little focal length here for my converging lens, and I'll just use a little arrowhead here for my antelope. But the antelope is going to make a real image. And so on the film or CCD array, the antelope's going to be upside down and smaller. We won't worry about the upside down, especially if it's a digital one, or even if it's a old-fashioned film. We can just turn that over when we want to look at the negatives, or we can display it on a computer, and the whole computer process will recognize that it's upside down and turn it over. So there is our lens. But of course, using this 1 over P plus 1 over Q equals 1 over F, you can kind of see now that if the antelope is then in motion, and I think it said towards the lens, so isn't converging lens, if the antelope runs, away from the lens, sorry. So maybe we spooked the animal and it saw us and ran away. Where would the image be? And so you can see in the math, and we talked about this for a camera, you got 1 over P plus 1 over Q, and then you don't change the focal length of the lens. And so as these change, and in this case, as P gets bigger, then Q has to get smaller in order for these two to still add up to the same number. And so what's going to happen is as this antelope moves away, and P is becoming bigger, the image then moves over here. And since your camera probably has a fixed position for the CCD array, you've got to kind of move the lens backwards. And so to keep a focus on the antelope as it moves away, the lens has to be in motion and kind of move back. Otherwise, it gets blurry. In fact, maybe you see that a lot in movies, and you see this in photography a lot, that maybe the subject is right here. So maybe you're like taking a picture of, I have many of these where, I'll be taking a picture of my kids, and so they'll be standing on the soccer field, and I'll say, "Hey, come by this way and stop right here and take your picture." And so I focus on them, and so they're nice and focused on my camera. But what that means is things farther away, and so the other kids on the field, or maybe the background has some trees or bushes, those are out of focus. And so you've got this nice picture, and it's a nice artistic effect where you have your subject in focus, and then the bushes, especially if they're like green bushes, they'll be blurry. And so you've got this spotty green background, and it looks really cool. And you can't really see the individual leaves, but then you can see the person really well. And so it's possible to focus on both of them. Now, there is a little plus or minus here. And so, especially when things are far away. If they're really far away, there's not much of a difference of a focus between something that's far and something that's a little bit further. So you can easily then, get a picture of maybe them running on the soccer field, and then beyond that, there's kids on the sideline. Those will look in focus, or almost in focus. If you look carefully, you'll see they're out of focus here. But for things that are, really close or make a difference, and that's the neat thing about taking a picture, like I said, with a telescopic lens, even though they're close, it's just nice to use a telescopic lens because everything in the background gets blurry. In fact, maybe you see that in movies. I like when they do that in movies where they'll have something in focus here and behind's blurry, and then they change, and then that starts to blur, and then this comes into focus. And I like that. I find it really interesting though. There's one of the Disney animations, and I want to say it's Lion King where they did that. They had like Simba here. It was in focus, and then they start to blur Simba, and then beyond it is like some antelope or something. Can't remember the scene exactly, but then they come into focus. And I remember seeing that the first time going, well, that is really cool, but it's an animation, it's a drawing. You can draw the two in focus. They didn't have to. So they deliberately went out of their way in the animation to make the drawing out of focus to act like it was a real image. And so it was pretty clever. Anyways, I digress again. So let's calculate this as they come back here to the problem here. Let's see, if the antelope is moving, how fast does the image move? And so what I'm going to do is take advantage of my Physics 121 and remind myself that there's a connection between position and velocity, and that's the time derivative. So I'll just take the derivative of this. And I'm going to think of this then as p to the negative 1 plus q to the negative 1 equals f to the negative 1, and then take its derivative. Because when you take the derivative, you get a negative 1 down in front, and then you subtract 1, so that becomes p to the negative 2, which I'll write downstairs as p squared. And then you'll have the chain rule, dp dt. And the same thing happens when I take the time derivative of q. So I get a negative 1, subtract 1, we get a negative 2, which I'll move it downstairs to get a q squared, and then the chain rule, dq dt. And here I'll just take advantage of what we said. The focal length is a constant, and take a derivative of a constant is always 0. And now I'll just kind of interpret this. This right here, this is the velocity of the object. This is how p is changing with time. And this then is the velocity of the image, how the image changes its position with time. And we are after, I believe, this. Come back to the question, how fast does the image move? Okay. So in order to solve this, I need these other pieces of information. So I'll start with the easy one. They say the antelope is at a position of 20. Now, it's starting to change, but at least at that moment, it's at 20. So I'll put a 20. You might remember these kind of derivatives from your calculus class, too. These are the relative rates. How does something change at a given position? So we are at 20. We know the focal length. So I'm going to use that to solve for what Q is. So Q is the reciprocal of F minus the reciprocal of P, and take the reciprocal of that. Okay, so the reciprocal of F. And maybe I'll do things in meters here, because they said the focal length is 30 centimeters. So that is 0.3, and I'll take the reciprocal. And then the object distance is the 20. So I'll take the reciprocal, hit enter, and take the reciprocal of that. And so the image distance is 0.305 meters. All right, so I need the P, and I also need the Q. Now, if I also need the velocity of the object, so I'll go VO. And they tell me that one straight up. They say the antelope, let's see, if the antelope runs, and this is important, away from the lens at a speed of 5. So the speed is 5 meters per second. I should probably check plus or minus. And so looking at my sign convention, if the antelope is running this way, right, it's going to bigger P. This is the direction of increasing P. So this is a positive velocity. And now I can solve. So I will put a negative for that negative. The P squared would be 20 squared. The rate at which the antelope is moving is a plus 5. If it'll be okay, at the same time, I'll move this to the other side, so that minus will become a plus. The Q squared would be 0.305 squared. And what I'm looking for is the velocity of the image. So going through a little bit of math here, I've still got my image distance. Let me square that and move it to the other side mentally. So then I can go times a negative 5 and divide it by a 20 squared. And so this is a velocity of negative 0.00116. And this is meters per second. Maybe I'll do millimeters. So this is negative 1.16 millimeters per second is how quickly the image is moving. And so if this has, a video camera in autofocus, we're going to need to be moving this lens, I guess, backwards, because this negative velocity means that the image is moving towards the lens. Remember, this direction is where Q increases. So a negative velocity would mean in the negative direction. So this image would be moving back. And to keep it on the CCD, we really want to move the lens this direction, towards the CCD. Anyways, I think that answers the second part as well. It says, does the image move towards or away from the lens? So it's moving towards the lens at a very manageable rate in terms of moving our mirror or our lens. We don't have to move it very quickly for a pretty fast moving object. All right, so there's number 2. Hopefully that gave you a little bit of insight. Let's see, next one on my list. 64. Printed that one up. Oh, it looks like it's magenta. I didn't notice that one. So this should be a challenging one. That's what the magenta color means. So let's be careful with this one and read it slowly. But we've got a figure. Okay, so here's what we're looking at. So somebody's looking something here. Shows a thin converging lens from which the radius of curvatures are, and they give us the 2 radius of curvatures. It makes sense. The first one here would be defined as a positive, and then the second one would be a negative one, and it looks like they're not symmetric. The lens is in front of a concave spherical mirror of radius 8. Okay. Assume its focal lengths, f1 and f2, are 5 centimeters from the center of the lens. Let's see if I'm reading that right. I think they're talking about the focal length of the lens, because we know the focal length of the mirror would be half this, 4. Yeah, I think the subject is always the lens. This is the lens, this is the lens, and just saying it's in front of the mirror. So this is the object of the sentence. Okay, so the noun of the sentence here is, the subject of the sentence is the lens. Okay, so that makes sense. So assume that its focal point is a little misleading. They almost sound like it's possible to have a focal length that would be different by saying 1 and 2, but they can't. They should just say the focal length, and there's one on both sides. Okay, but anyways, they're telling us the focal length of the lens, and indirectly the focal length of the mirror from the center of the lens. Determine the index of refraction. Okay, I see what they're after now here. So, okay, so if I put here for A, I know that 1 over the focal length is equal to n minus 1 times 1 over r1 minus 1 over r2. And they gave me the 2 radii of curvature. They also gave me the focal length, and therefore I can solve for the index. So 1 over f. F, they are saying it is 5. Let's see. Why don't I do everything in centimeters, and they would cancel, and I would get n, which is just a number. So I can leave them in centa. So this is 1 over 5 here. This would be an n minus 1. And radius number 1, they said, was 9. And radius number 2 is 11. And it's a negative 11. Again, that first curvature, as the light comes this direction, would be a positive, and that direction would be a negative. And in fact, this is a good example that if it, switched the order, we would come light this way, and we would hit this surface first. And so then we would have a positive 11 minus then a negative 9, and that would be the same mathematical piece there. So we switched what's 1 and 2, and we switch from everything from positive to negatives. So I can solve this. So grabbing my calculator here, let me take that number, which is a 9 reciprocal. The 2 negatives make a positive, so I'll go plus 11 reciprocal, and enter. And so that's that together. And let's see how best to do this. Why don't I bring this over, think of it in the top, and I'll put it times 5. And so that's there at the bottom. And so then when I take the reciprocal of this, I'm at 0.5 0.99? Whoa. Okay, I guess it's reasonable. It's a pretty high index, but we can have a high index, I guess. So 1.99 for the index of whatever this material is. And so this is high index glass. Usually glasses are more like 1.5, and even some of our lead glass is 1.6. So it's pretty on the high side, but not impossible. Okay, so assuming that determine the index of refraction. B, the lens and the mirror are then 20 centimeters apart, okay? And an object is placed 8 centimeters to the left of the lens. Determine the position of the, oh, here it is. Here's why it's magenta. The final image and the magnification as seen by the eye in this figure. And is the final image inverted or upright? Please explain. All right, so let's run through the math. But the reason I wanted to do this one was because it had multiple lenses or multiple optical elements. Because, as I said, the way to handle these is you just do it one by one. That is, you figure out where the image of the first one is, and that image now becomes the object of the second one. Now, in this case, I think they gave the magenta one because once the light hits the mirror and bounces off, it's going to go through the lens a second time, and that's kind of like a third element. So there's really three object and images we've got to work with here. So we've got the lens acting as creating a first image, then a mirror creating a second image, and then the second image actually becomes the object for the lens again as it goes back the other way. And that could easily be overlooked. So we've got to do this 3 times. So let me go 1 over P plus 1 over Q is equal to 1 over F, and let me just find P here to begin with. So in terms of the focal length, it is 5 and reciprocal. Let me then subtract where the object is, the P, and that's, they said it was 8 to the left. Let me just double check that. The lens, the object is placed 8 centimeters to the left of the lens. Okay, so minus 8 reciprocal, and then taking the reciprocal of that gives me a distance of about 13.3, and I'll call this magnification number 1, because that would be minus 13.3 over 8. And so divide that by 8 and put a negative in front of it. So that's 1 2/3. Okay. Now, on my diagram here, maybe I should put where it would probably be. But if I come back to my drawings, we're looking at a scenario that I think is this one. Yeah, it must be the one that is greater than 1 focal length, because that's 5, but less than 2, and that's 10. So what we should get is upside down, so our magnification should be negative. So sure enough, it is negative. And it should be bigger or greater than 1, and so sure enough, it is. And so Q magnitude should be a little bit bigger than P, which remember P was 8. So all that lines up. So I would say what we've done right now is kind of created this. And if I put it in my drawing somewhere, this distance should be a 5, and this distance should be a 4. Oh no, radius of curvature would be 8. The focal length is 4. So they've got this at a 4. I'm in an 8. The whole distance is a 20, so this is at position 12 from here, if you will. Maybe I shouldn't draw too much, but we've discovered that it's at 13 And so it's right about here. So it's 1 2/3 bigger, and it's inverted. The light has come through, and now this light's going to come through and hit this mirror. And so I'm going to go back to the drawings we did for the mirrors. So here's the mirrors. And so I think I'm looking for the mirror at this scenario where the object now is going to be between the focal point and the center of curvature. Let me just kind of confirm that. This is just, yeah, because remember the focal point would be, you know, at this 4, if you will, measuring from here would be a 16. And so this right here at 13.33 definitely puts the image that's created by this lens at a spot that's between the focal length and the center of curvature, or twice the focal length. So we're between there. So what should happen is this should then reflect off and create an image out here that is also inverted. So now it's going to be a net effect of being upright. And it's going to get bigger yet again. And so let me run through the numbers. So maybe I'll put kind of a line here and say this is number 1. This is what happens to the object in terms of getting bigger and inverted in its position. So if I call number 2 case 1 over P plus 1 over Q equals 1 over F, and I solve for Q, now we're looking at the light coming off this concave mirror. And so it would be the reciprocal of F minus the reciprocal of P, and then take that reciprocal. And F then is a 4. It's half this radius of curvature. And its position, and this is what we mean by the phrase, the image of the first optical element becomes the object for the second. And so I need to figure out how far is this image from the mirror. Notice I'm not using 13.3 for the P. That's the distance it is from this lens. But now I want to know the P for number 2. I guess we could even put, like, you know, number 2s here. And say how far then is this from number 2? And so this would be the 20 minus this, which makes it what, 6.666, I'll call it 667, because that distance, the 13.3, and this got to add up to 20. And then hopefully I'll get, as we talked about, a positive number out here that's going to give me then a quite large, and I'll put magnification right here, minus a Q over a P, to see what I get there. Okay, so grabbing my calculator here, let me go for reciprocal minus 6.6666666 reciprocal, hit enter, take the reciprocal of that, and we're looking at a distance of 10 centimeters. Okay, good. Now, let me say again, notice it's positive, which does match kind of what we said here, that it would hit it and bounce off and be someplace a little further out and therefore a little bigger. So our magnification should be a negative and greater than 1. So I'll take the negative 10 for the minus and then the 10 and divide it by the P, which we said is 6.6666666. And so it looks like negative 1.5. And I'll call that magnification number 2. And I'll say it again, this is probably why the author labeled this as a magenta one. I can see many people stopping right there and then maybe saying, well, the total magnification, so if you got this much bigger and then this much bigger again, you just multiply those two together. And sure enough, a negative and a negative make it positive. Each one inverted it, and you're kind of done. But it is going to go through the lens again. So maybe I should draw where this second image is formed. Maybe I'll do that in red. But it looks like it would be right about here. And it's 1.5 times bigger than that one, which is already bigger than the original. And so light would bounce off and be right here. See, and then that's what I'm saying. This light now is going to go through this lens a second time, making a third optical element. And at this point, we're at 10. Ooh. And 10 is twice the focal length. Oh, that's kind of nice. Okay. Because twice the focal length for a lens is that transition. So we're looking kind of at a transition between being further than 2 focal lengths and at 1 focal length. So we're at a transition from getting something inverted smaller and inverted bigger. So what we're going to get is inverted same size. And so I'm quite sure that what I'm going to get is inverted. So this will be the third one. Oh, I better do the math. And same size, and so the magnification this third time going to come out to be a 1. But I better do the numbers here. So, all right, let's run through the numbers. And so number 3. And so again, I'll go 1 over P plus 1 over Q is equal to 1 over F. We're trying to solve for Q. And so that means take the reciprocal of F minus the reciprocal of P and invert that. And so as we go through the lens again, we have a focal length of 5. And we've discovered that the Q, and I want to be careful here, the Q is a 10. So that means it's 10 from this mirror to here. What I want then is the distance from this red one to the mirror, which actually comes out to be another 10 because the total is 20. So I don't want you to think I'm using a 10 because of this 10. I'm using a 10 because of this 10. So it would be 10 inverted. And that must come out to be 10, right? 5 reciprocal minus 10 reciprocal. That is a 10. So notice it's a positive. And then the magnification, let me call it magnification number 3, would be then minus this Q, which is 10, over this P, which is 10, which is negative 1. And so it does match what I was kind of saying. They gave me the third one, the easy scenario, where the math works out, where you just invert it, it just becomes a negative. And there's the final image. So let's come back to the question here. I guess the first one I answered, which it said, what is the index? We did that early on and got something